Okay, welcome back to the Biomechanics Remote Teaching Lab. Today, in this video, I'm going to go over angular impulse, angular momentum relationship, and I'm going to talk about springboard diving, or actually it's not springboard diving, but it's pretty darn close. So I'm going to go ahead and share a screen. You should have already watched the lecture on angular impulse, angular momentum. You need to have done that in order to follow along in this video. So I'm going to go ahead and share the screen with you on some video that I shot for watching a Cirque du Soleil practice. And this is the swinging chair. Oh goodness, I forget what they call this, the Russian swing, I think it is. Maneuver. And what I'm going to go through is the relationship of angular impulse, angular momentum. From the context of once this person, this is going to be the diver right here, leaves this swing. And then we're going to talk about the angular velocity that she undergoes during this maneuver. So let's watch it first, and then I'll go back and play it. This looks like a lot of fun. You get the swing going, off into the air, super high, and into the water. I've got another one there. I'll show you that. Let me go back. All right, so let's just look at her angular velocity during the dive. She starts off spinning and clearly slows down angular velocity near the end of the dive. So in the beginning, right here, she's spinning with some velocity, but near the end here, that velocity is slower. So in the previous lecture, we talked about the math behind how angular velocity is changing during the course of this dive. Let's freeze it right here. Here she is in the air, and we do a kinetic analysis on this movement in the air. The only force acting on the diver is gravity, and gravity is acting at the center of mass of the person, and the person is rotating around the center of mass. Therefore, the force of gravity is not contributing any torques about that axis of rotation. So angular impulse, torque times time, is zero. What that means is that the change in angular momentum is going to be constant. The change in angular momentum will be zero, which means angular momentum will be constant. What's angular momentum? It's moment of inertia times angular velocity. So if we multiply her moment of inertia times her angular velocity at this moment in time, that product will be the exact same as this moment in time. Moment of inertia times angular velocity. The angular momentum here is the same as it was a few frames back, because the difference in that angular momentum has to be zero, because there are no external torques acting on the system. All right, now she's spinning with some velocity here, but as we saw, she's rotating much slower here than back when in the pike position. Why? How is angular velocity changing? Well, her moment of inertia is much greater here. Therefore, the product of moment of inertia times angular velocity has to be the same as back here. And if her moment of inertia is greater, that means angular velocity has to be lower. Okay? So the product of moment of inertia and angular velocity has to be constant. But in this case, moment of inertia is greater than a few frames back. Let's go back here. Moment of inertia is lower, therefore angular velocity is faster. And we see that she's spinning faster here than when she spreads out into a layout position. That is all because the angular impulse momentum relationship is such that there's no external torques acting on the diver, therefore there's no angular impulse, and therefore angular momentum is conserved. It's constant. All right, so let's look at this one. I'll come back and look at it again in just a second. Let's look at the next one. Same sort of task. Oh, there we see lots of change in angular velocity. That's pretty cool. That is really amazing. All right, let's go back a little further. So here, let's just look at angular velocity. From the moment this person leaves the swing, spinning fast here, then the diver is going to open up, velocity is going to slow down, and then he's going to go in the tuck position and speed up again. And then finally open up again and slows down. So let's look at angular velocity again. Angular velocity, from the moment he leaves, speeds up, slows down, speeds up, slows down. Why is angular velocity able to change when there's no external torques acting on the system? It's all manipulation of moment of inertia. Moment of inertia is small here. We take the product of angular velocity times moment of inertia at this moment in time. That product will be the same as right here. This is a bigger moment of inertia because there's more mass further from the axis of rotation, and therefore angular velocity is lower. Why? Because angular momentum is conserved, it's constant. There's no external torques. The difference between angular momentum at time 1 minus time 2, the difference is going to be 0. That means that the same angular momentum has to exist at time 1 as time 2. So now he's opening up, he's going to slow down, and then goes into a tuck again, speeds up and slows down, all because of a manipulation of moment of inertia. Now the key with understanding this during the flight is that we're only concerning ourselves when the person is in the air. If we're dealing with the person in contact with the swing, we have another force acting on the diver, and we need to account for that. In our equation, sum of torques times delta T equals delta I omega. So the whole trick with getting really good at diving is to get the right angular momentum at the moment the person leaves the swing. Because once the person leaves the swing, the amount of angular momentum is determined. The angular momentum cannot change because there's no external torques acting on the system. Up until this point, the person's still pushing on the board, on the swing, and can manipulate angular momentum. So these divers are really practicing getting the right angular momentum at takeoff. Once they have the right angular momentum at takeoff, then they can perform the trick as to the best of their ability. And same thing on the other one. Once the diver leaves the swing, right here, actually where I stopped it, he's already left. But up until that point, there's another force acting on the diver, and we need to account for that. But once the diver leaves the swing, the only force acting on the diver is the force of gravity, and that's acting through the center of mass, and the person's rotating about the center of mass, and therefore there's no new external torques, and angular momentum is conserved. It's controlled, it's constant. That means this diver needs to practice getting the right angular momentum at takeoff in order to manipulate and successfully perform that task. Okay, that's it for this one. All right, thanks everybody.